Okay, thanks. So tonight I want to talk a little bit about the science and engineering of the James Webb Space Telescope. I always caution people when I give these addresses as a solar system ambassador that I'm not an expert, I'm an enthusiast. But one good thing about presenting to a group like this is that I know some of you are quite familiar with the James Webb. So if we have questions or discussion as time goes on, there may be some of you that can answer questions that I can't. So let's go ahead and get rolling. Okay, so the presentation is kind of divided into two parts, one on the telescope and one on some of the first images that have come from the telescope. So we'll talk about the telescope first. So first of all, kind of the tail of the tape. The James Webb Space Telescope is by far the biggest space telescope that's ever been put into space. Some measurements, it's about 69.5 feet long, about 46.5 feet wide. If you look at the aluminized sun shield there, that's about the size of a tennis court. If you're looking for something that you can relate to. It has a height when extended of about 28 feet. So that's about a 3-story building. Or as seems to be common in a lot of space Twitter now, it's about the height of a giraffe. So everything seems to be measured in giraffes lately. Okay. It does weigh about 13,700 pounds. And all of that telescope had to be folded and squeezed and rolled up to fit inside an Ariane 5 ferry, which is about 17.5 feet across and about 56 feet long. And in order to deploy from that folded stage, there were about 300 separate motions and actions that had to happen. They were all single points of failure, which meant that if any of those didn't work, then no telescope, or at least a pretty seriously impaired telescope. Okay, next one. So just a few more photos to give you a sense of scale. The one on the left-hand side is a representation of the James Webb folded up and in the ferry. So that's what it looked like before launch. Second one over, just to give you a scale with some humans as to how big that thing is when it's fully deployed. And then up on the extreme right, that is the little tiny thing you see in the middle of the mirror called the aft optics subsystem. That is a technician beside it, so you can tell how big that is. And that one was kind of a meme for a while when they were making sure that they removed the lens cap on the before this. Okay, next one. A lot of people want to compare it with the Hubble because that's most familiar to folks. So here's a quick comparison with the Hubble Space Telescope. The Hubble is also quite large. Yeah,
sorry,
hey,
running late.
Oh, good.
Tardy.
Yeah, you're just getting rolling, so you're in good shape. So the Hubble Space Telescope is about the size of a bus, so it's not small either, right? And has a mirror diameter of about 8 feet. So that's kind of a measure of its light gathering power. The James Webb, on the other hand, talked about its measurements before, so quite large, and a mirror diameter of about 21 feet. So a lot more light gathering power. Okay, excellent. So whenever you talk about any telescope, there are kind of 3 things that are most relevant or most interesting about a telescope. So the first one is, what kind of light is it designed to intercept? And of course, here on Earth, when we look through telescopes, it's all visible light. But there are lots of different kinds of telescopes on the ground and in space. There might be gamma ray, X-ray, radio wave, ultraviolet, infrared, and visible light. So the James Webb is different from the Hubble in that its focus is near infrared and mid infrared light. And we'll talk a little bit later about why that's important and why it's useful. So it collects in this range, which you won't remember, but it's a 0.6 to 28 microns wavelength. The Herschel infrared telescope, which was a European Space Agency product, was in the far infrared. So it was actually quite different in what it was observing. And the Spitzer infrared space telescope, which just shut down a few years ago, was more or less in the same range as the James Webb. In terms of light gathering power, because the James Webb has a mirror that's about 6 times larger than the Hubble, it is about 100 times more powerful in terms of its light gathering or electromagnetic radiation gathering power. So it's like anything you might look through. If it's bigger, you can see more light through it, right? So it collects more. And then the final thing, other than what kind of light does it look at, and what's its light gathering power, is what's its resolution. So how small or how close together can 2 objects be, and you still be able to discern them with your telescope. And so the James Webb has a resolution of 0.1 arc seconds, which is one of the measures of resolution. Compare that with the Spitzer Space Telescope, same infrared light, but 2.5 to 16 arc seconds. And so on the bottom right photo, you can see an image that was taken from the Spitzer and the same area taken with the Webb. So you can see, I mean, the clarity and the ability to separate things are quite amazing. Incredible. Yep. We'll talk a little bit more about the top image in a bit. This is a comparison of looking at an object with visible light on the left-hand side and with infrared on the right-hand side. And you'll see later when we talk about it that the ability to see through space dust is really enhanced with infrared. Okay. Another representation of kind of the power and the application of the telescopes. The size of the box that you see on the screen is kind of how much light is being gathered by the instrument. And then from left to right, this is just the wavelengths that, whoops, sorry, back up one. I think I touched, yeah. Is the wavelength that's being looked at. So if you compare that with the Hubble Space Telescope, it kind of looks at some ultraviolet, visible, and a little bit of infrared. And compare that to the Spitzer Space Telescope, had a pretty big overlap actually with the Webb. But you can see with the Spitzer, not a very big mirror at all. And so you can see it's not gathering very much electromagnetic radiation. So talk a little bit about maybe more engineering than science of the Webb. One of the things that's most apparent about the James Webb Space Telescope are those gorgeous mirrors, right, that are used to collect the light. There are actually 4 different mirror systems on the Webb. The one that's the biggest and that everybody sees are the primary mirror. So there are 18 hexagons of mirror, total of about 21 feet in total diameter. Each of those weigh about 46 pounds. And, you know, since they're close to 4 feet across, that's, you know, not exceptionally heavy for something that size. And it's adjustable. And we'll talk a little bit about how adjusting is done in the next slide. The secondary mirror, which that's the primary mirror. The secondary mirror, which it focuses on, is about 2.5 feet across. And then inside that optic subsystem, that black box that I showed you before, there's a tertiary mirror or third mirror, which is used inside. And then there's also a fine steering mirror that's used to help guide the telescope. So you don't see those final 2, but there are 4 mirror systems on board. Okay. So a little bit about the construction of the mirrors, because I think it's kind of interesting. Should work now. Thank you. So 3 questions: why hexagons, why gold, and then the substrate that the gold is sitting on is beryllium. And I'll talk a little bit about why beryllium was selected. So why hexagons? Well, the first thing that they wanted to do when they designed the telescope was attain something that was approximately round before they sent it up, because that was the easiest way and most efficient way to gather light and then focus it on something. There wasn't a lot of waste in that way. Second reason why that was selected is that it allowed for not having much space between the mirror segments. They could have selected round ones for each of those 18, but then you have all this blank space around them, and you kind of waste some space in that way. From an engineering perspective, more difficult probably to make them hexagons than circles, but the choice was made for hexagons. And then the third, which I really don't understand that well, is that by choosing hexagons, they only had to think about 3 different kind of prescriptions for the lenses or for the mirrors in terms of how to make them and how to do the curvature. So it did simplify the creation of the mirror by making them hexagons. So you'll sometimes see in some of the representations, you know, when the James Webb was getting hit by some micrometeoroids early on in the flight, they talk about, oh, that only affected a C segment mirror, so that's not as important as if it had hit a B segment mirror. So there are 3 different types.
So before you go on, talk about micrometeors, you know, that's constant.
Yes.
So how do they deal with this on a constant basis?
Yeah. So first of all, the sun shield is designed to intercept a lot of them that are at least coming from that direction. So it kind of cuts the risk in half. The ones coming the other way, they're just going to have to deal with it. They're going to have to get hit. They've had a couple of small impacts, one that was not so small, And if the impact is strong enough to knock one of the mirrors out of alignment, they can realign them. There are actuators on the back, and they can even change the curvature of each of those segments a little bit. And then finally, failing all that, if you get a big enough hit, they can do a little bit, I think, with the programming to kind of compensate for the irregularity in the mirror.
Yeah, another naive question.
Yeah.
Can they close it down if they have to?
No,
If there's a big strike coming?
once it's open, it's open.
Okay.
Right? Yep. And of course, as many people know too, it's not in Earth orbit, it's way out there. So there's no way to go service it, right? That we know of anyway. It's got to work.
It'll be like an astigmatism, like just that one part
Yeah.
would be kind of blurry, and then the computers can
Yeah,
figure it out from there.
right. You got to program it. Yeah, cool. So that's the hexagon shape. Second question, why gold? Well, the simplest answer is gold is a very good reflector of infrared light, better than silver is. So that's why they chose gold instead of a silver coating. There's not much gold on those mirrors. It's vapor deposited. So they put these beryllium blanks inside a vacuum chamber and then they vaporize gold. And so it's only, I think, a couple of angstroms and maybe 800 atoms thick. It's extremely small. I think I read somewhere if you scraped all the gold off all those mirrors, it would be about the size of a golf ball, maybe. So there's not a lot there. Okay. And so speaking of scraping it off, what are they scraping it off of? So the blanks are made out of beryllium. And beryllium was chosen as a metal for 3 reasons. It's really light, it's really strong, and it doesn't expand or contract a lot when it's subjected to hot and cold temperatures. And so they want to eliminate any kind of waviness that might be happening in the mirror, since they're so sensitive to infrared light. So they chose beryllium as the substrate. So these mirror segments were cast as one. They were sliced down the middle to make 2 of them. And then they were polished. So that's the polished part of the mirror, is the beryllium base. And then they vapor deposited gold. There wasn't really, as far as I know, unless someone else knows, I don't think there was any polishing of the gold once it's on. That's done. But something I also learned recently is gold's not the last layer. They actually deposited some glass on top of the gold in the mirrors to protect it from micrometeoroids for one thing. So they cast the sheet, cut it in half, and then drilled out the back to make it lightweight. And with that pattern, it still remains very strong and unlikely to bend. And then finally, as I mentioned, they are movable. So there's 6 actuators on the back of each mirror, and that's used just to turn them in whatever direction. And they had to turn them to get them accurate and all lined up on the secondary mirror to a point where far less than the diameter of a human hair was the precision with which those had to be moved. And then it might be difficult to see, there are struts that run out to the corners, and that's used to affect the curvature of the mirror. So they can actually change the curvature. They can adjust that. They can adjust that. Yep. And that's what a lot of that almost 3 months of the commissioning phase was, getting these mirrors lined up and correctly done.
I see the Ball Corporation.
Yeah.
I think of them as canning jars, which obviously they do a lot more than that. But
So
they made the mirrors themselves.
So the Ball Corporation, I think, was mostly involved in gold plating. And then there was a mining firm out in Utah that did the smelting and the casting and the sawing.
It's kind of like Playtex making the plate space.
Yeah, yeah,
for
right.
television,
Right,
right?
okay.
You don't think of that brand of space.
Right.
Okay, good. All right, so that's the mirrors. That's one of the most visible and kind of iconic pieces. The next is sun shield. I mentioned about the size of a tennis court, so 70 feet by 47 feet. It is kite shaped, and I'll talk a little bit about why. And it has 5 layers of Kapton film. And we'll talk a little bit more about Kapton and why it was selected. All 5 layers of this basically plastic Kapton film has been aluminized. And then the 2 sides that face the sun also have silicon put on them. And I'll talk a little bit about why. It's really thin stuff. I've got a sample of aluminized mylar here that I'll kind of pass around. You can take a look at. This stuff is a lot thicker than what's on the James Webb. So I think you'll be kind of surprised if you pass that around. This is not thick stuff.
They kind of equated the Kapton to mylar.
Yes, yeah, very similar. In fact, before I came, I wanted to kind of remind myself of the distinction between the 2. They're both DuPont products. One is more of a polyester, the other one is kind of a polyimide film. Kapton is a little stronger tensile strength, and it probably can withstand being out there longer than Mylar could. So it's very thin, but because of that and the micrometeorite risk, it is rip stopped about every 6 feet. So if it does get a rip, it'll rip out to a seam and stop there. So that does provide some of the protection. And the sun shield's value is to keep the mirrors and the instruments cold, because it's looking at infrared. Infrared light is like heat, right? So it has to be shielded from the sun and the inner planets, or as I think I read somewhere, it'd be like taking a camera for visible light and making it out of flash bulbs. All it would see is itself, right?
Or shooting it right at the sun.
Right, or like pointing it right at the sun, exactly. And it does provide significant insulation. So these 5 layers of this really thin stuff, spaced out about 8 inches apart, keeps the warm side of the telescope at about 230 degrees Fahrenheit and the cold side at about minus 394. And I've read a couple of numbers in the last little while. The one is that if it was a sunscreen, it would have an SPF of a million. And then I heard a NASA guy on TV yesterday said if it was a sunscreen, it'd be an SPF of about 10 million. So whether I could tell the difference, probably not. So that's pretty cold, minus 394 degrees. For one of the instruments, that's not cold enough. And there is actually, aside from this passive cooling, there's active cooling where they're actually sending in cooling to keep one of the others.
It's hard to believe that can't be cold enough.
It's hard to believe, right? Because I mean, it's not exactly right, but at absolute zero, which is only about 10 degrees away, electrons stop moving, right? So I mean, that's cold. All right, so why Kapton? It's really light and it's really strong. And it probably withstands a wider temperature range than that Mylar that was passed around. The aluminum is sprayed on it, so it's reflective, so it reflects the radiation back into space. And the silicon that's on it reflects even more, and that's why it's on the 2 sun side facing layers. I don't understand electronics, so maybe someone here can help. It's doped silicon so that they can actually, if there's any static electricity or anything that builds up on it, they can actually take that and it's grounded to the frame. Does that sound about right? Yes. Sound about right. 5 layers. 5 layers is just that every layer provides additional protection. And why are they spaced out? Because if they took it 5 times as thick and put it all together, it would conduct that radiation. So they put that space in between, because in the vacuum of space, it's a nice insulating layer in between. And then finally, why is it kite shaped? It's kind of designed with a particular shape and variation in the spacing between the layers, so that as the heat does come through, it's moved out to the outside of the telescope and beyond. So it's to prevent any kind of accumulation from in close. And then you can kind of see what the deployment process looked like. That was probably 200 of the 300 moves that the telescope had to make when it deployed. Okay, so the next part I won't talk about a lot, but I mean, it's all held together by something, and it's either called the support structure or the backplane. And so it has to be really light, but it has to be really strong. It holds about 5,300 pounds of hardware, including the mirror, aft optic subsystem, the board cameras or instruments. And there was a tower array on it because it was kind of squatted down, all the mirror stuff, until it got into space, and then it extended up to get out of the way of the sun shield. So all that had to be held on this backplane, almost all carbon fiber structure. So graphite with titanium and what's called in-bar steel fittings. In-bar is a kind of steel that doesn't expand and contract in alloy. An alloy doesn't expand and contract. Used in airplanes all the time. Okay. And then the instruments. And I'm not going to spend time on the details of the instruments, but there are 4 cameras and systems that each have their own particular application and use on board. So this is kind of unique among some of the space telescopes and the number of different instruments that are on board. So there are 3 that work in infrared called NIRCam, NIRSPEC, and NIRIS. And then there's this one that deals in mid-infrared called MIRI. They are products of different countries. NIRCam, almost all kind of a US NASA product. Near Spec was a joint venture between NASA and the European Space Agency. MIRI is joint between the European Space Agency and Jet Propulsion Lab. And then NEARIS is a Canadian Space Agency product. And these cameras all do different things. So there are kind of some common elements that are in many of the instruments, and then there are some that are really unique. So the ones that are common that are in a lot of different space telescopes, cameras, all but one has a camera. The spectrometer doesn't have a camera on board. Near Spec, spectrographs to break light into its respective wavelengths, coronagraphs, which can be used to kind of dim some parts of an image so that you can see a dimmer part, or bright part so you can see a dimmer part beside it. Filters, just think of those as like filters on your camera to either filter in or filter out different kinds of light that you may want to look at. They're usually on a revolving wheel so they can be spun into place. And then sensors of some kind or other. Think of the CCDs on your camera. That's kind of how you should think of those. And then there are three that are really kind of unique. So on the spectrometer, Near Spec, it's got what's called a micro shutter array. And as I read more about this, it's got to be the most amazing thing. So it has 4 quadrants, each about the size of a postage stamp, with about 60,000 little louvered doors on each. So in total, what's the number? 248,000 tiny doors, each about the width of 2 hairs. And they're used to mask off or select parts of the image to let the light come through and then measure its spectrum. And so they take a look at the image that they want to look at. They determine which of the doors they want open and which they don't. And a magnetic bar sweeps across these doors and opens some and leaves others closed to get the exact right which they want. It's amazing to do, right? By doing this, they can look at 100 different objects simultaneously and determine their spectra. So that's incredibly powerful, efficient work to be able to do that. Okay. There's another one called an integral field unit, which in a way is kind of similar. It allows you to take an image and then take it elsewhere to split it up into its respective light spectra and then put the image back together to look at. So kind of incredible. And then the aperture mask is used to kind of hide different parts of the mirror, and you can get better resolution. If any of you know about radio telescopes where they have these arrays where they're kind of like miles apart, it's like a mini interferometer on the machine itself. Pretty incredible. Okay, and then lots more that I won't talk about, but on the sun side of the sun shield, there's all sorts of other stuff going on there that if you want to talk about later, we can talk about. But there's a thing called a momentum flap, solar panel, power management, active cooling, antennas, star trackers, propulsion, data handling, and communication. All that's on the sun side because it can operate in that heat out there. The momentum flap, I just find kind of personally interesting. If you look at this little paper model, you can see this little flap on the back side of this. And I always wondered what the purpose of that was. Well, it turns out that the sun shield, the center of it is not in the same place as the center of mass of the telescope. So as that radiation comes in, it can turn it a bit. So it kind of acts like a trim flap, right, on the telescope. So it saves them from using valuable propulsion fuel to keep that going. Okay, so that's the telescope. And now we'll move to the science. So we talked a little bit about infrared, and some of you may have the question, so why infrared? Why do we want to look at things in infrared? And there are 2 primary reasons. The first is that with infrared, you can see through dust. And in one respect, there's a lot of dust in space, although space is mostly what? Space. But if you're looking through 13 billion light years of it, that's enough to look through. So if you can find a way to look through that dust, you can see what's beyond it. And so the way I like to think of it is if you have a really smoky campfire, you might not be able to see the flame, but you can still feel it, right? And so that's kind of what that infrared is attempting to do, is to see through that dust and see more. And so you can see an example of looking in visible light at something in space and then looking at it in infrared. You really can see through. through that dust. The second reason for looking at infrared is about Doppler redshift. So you know that when an ambulance or a train goes by and you get that sound that increases in frequency until it gets to you, and then it goes down in frequency as it goes by. Light does that too. And as the universe is constantly expanding and expanding at a faster rate, you can see further into the past and more distant objects if you can see that light, that visible light that's been stretched out into infrared and far infrared. So what can you see if you look there? Cooler stars, red giants, planets, comets, and asteroids at a much greater distance, dust that's been warmed up by starlight, protoplanetary disks, or the stuff that's kind of getting together that wants to make a planet and hasn't done it yet, even emissions from cold dust, okay? And in very cold molecular clouds. So the Webb team is expecting to see things that we've never seen before at a distance because of the resolution, because of the amount of light that you can gather, and the fact that you can see this redshift. Another kind of interesting thing before we get to the images is, where is it? So a lot of people know it is about 1 million miles from Earth, not in Earth orbit or a more distant Earth orbit. It is out at what is called one of the 5 Lagrange points that you'll find around any two orbiting bodies. So Sun here, Earth here. There are several Lagrange points to select from, and it's chosen Lagrange point L2. So why would you want to stay at a Lagrange point? Because you don't have to spend a lot of energy keeping in that orbit. It's a stable orbital location. So you don't have to use a lot of power to keep it there. Now, L2 happens to be one that's called metastable, in which you have to apply a little bit of propulsion from time to time to kind of keep it where it is. It's not going to stay perfect. But the good news is that the European Space Agency, with their Ariane rocket, put it exactly in the right place when it went, and has conserved about 20 years of fuel on board the James Webb. So if things went about average, it would have lasted 10 years. If they had to do some work to get it to the right spot, maybe 5 years. If everything went perfect, it would last for 20, and it's 20. So that's good news. So if you can imagine, if my head was the sun and my fist was the Earth, then the James Webb Space Telescope is in this L2 orbit out here, right? But it's not directly in line with Earth and the sun, because then you'd have to try to communicate through Earth. So it actually travels in an orbit, in a halo orbit that goes around that. So it's always in communication, and it's not blocked by the Earth for that purpose. And you'll also notice sunshade pointing toward the sun, so the mirrors and the instruments are out. So how does it look at all the sky? Well, as it's going around the sun and around the Earth through that, it aims its mirrors around so it can see as much of that sky as possible. And it's going like this, right? So it's spinning around. And in that way, you can get pretty much all of the sky twice in each year. So that's the method behind the madness. 4 general categories of what the scientists want to look at: the life cycle of stars, what happened in the early universe, how do galaxies evolve over time, because now we can sample everything from like the very oldest ones to ones that have been formed fairly recently. And then the last one, which maybe isn't talked about a lot yet, but will be, I think, as time goes on, is other worlds or exoplanets, planets around other stars. So now we'll get to some of the images. I imagine most of the hands will go, but who's seen kind of the first images and some of the information? So some of this will be a repeat. Hopefully I can add a little bit of new information that's been learned since some of the first images. But this first image is one of what's called SMACS 0723. It's a galaxy cluster. And so the galaxy is kind of in the foreground. The other thing that's kind of neat about this is that anything that has these spikes on are stars. And those spikes are created kind of as diffraction as the light goes off the edges of the hexagons and off those 3 support arms. And they're kind of unavoidable, but they did some neat design things to at least keep it down to 8 8 spikes. So each of those are a star. Everything else in there is a galaxy. And that's really kind of incredible, that many galaxies, especially when you consider that the area of sky that that image is looking at is about the same as if you took a grain of sand and held it at arm's length. That's about the portion of the sky that it's looking at. Right?
You know, it's funny you show that because, you know, Al Ward has been here many
Yeah.
times. Al told me something a long time ago that I never really could grasp because obviously we've never seen it, but you know, when he orbited the moon, everything went to the dark side of the moon. Right? Well, the sun, it's not very much something on the dark side, but the unsunlit side, you can say shaded by the moon. You can't see the sun, it blocks the earth of the moon.
Yeah.
It's pitch black. He said space is white. Space is
Yeah.
not black.
Yeah.
So if you look out there and you think space is black, it's so there's so many stars. Yeah, they're being shielded out, we can't see. He goes, it's just all white.
Yeah.
That's how bright it was.
Yeah. Another thing interesting about it is you see these kind of arc-shaped things. This is kind of evidence of and proof of gravitational lensing. So the objects in the galaxy, their gravity is strong enough that the light coming from things behind it is actually bent by the gravity of those galaxies and large items in front. And I'm always interested in gravitational lensing around black holes as well, as that's one way to find black holes. If you've got these things being bent and there's nothing in the middle, well, there's a pretty good chance that that's what you're looking at. I can't remember exactly which two they are. I think they might be these two on the left-hand side. So that's actually one galaxy that's the light's been bent and you see it twice, right? So that's I think, pretty interesting stuff. Okay. So, and then the final thing about this image, I think, is that the very dim red things are galaxies that are way out there. So pretty close to 13 billion years ago is when that light left those galaxies. And it's taken 13 billion years to reach. And I always find that amazing about anything in the sky, right? Is when you see something up there, that's not what it looks like now, and that's not where it is. It's just, it just took that long to wait to find it. Okay. Tony and I were mentioning this, after the first images, you saw a lot of comparisons of Hubble and James Webb images, right? Because of the light gathering power and the size of the mirror and the resolution that is achievable. I mean, it's showing us some things that clearly Hubble could not. On the other hand, I think it's also fair to point out that comparing Hubble and JWST is not really quite fair. They're different devices that are made for different things. So here's a Hubble Jupiter image on the left and a James Webb Jupiter image on the right-hand side. You say, well, that's not that impressive. And I'm really kind of fortunate that the presentation is today because someone took some of these Jupiter images and reprocessed them, and they're pretty darn good. But still, I think it's fair to say they're really made for different purposes, so it's not totally fair to compare the two. Right. All right. Second image, maybe one of my favorites, is a set of 5 galaxies. It's known as Stephan's quintet. It's been known for quite a long time. There are actually 5 galaxies in this image. So there's one at the top, 2 that are interacting below it, 1 further down, and then 1 on the left. First thing to note, the one on the left is really way in the foreground of the other ones. So it's not involved in any of the interactions going. It's up here and the other ones are out behind. These 2, though, are interacting, spinning together. We don't know exactly how they'll interact. It's really complex modeling to know what they'll do. But you can see this rim of red above the 2 galaxies that are interacting. Those are star-forming regions caused by the shock wave of those 2 galaxies colliding. And it's sending a shock wave through the gas, and the shock wave through the gas is enough to make the stars light up. Right? Okay. The other reason I like this one is that my favorite holiday film is It's a Wonderful Life. And if you remember the scene where the 3 angels are deciding which one ultimately to send Clarence down to Earth, it's Stephan's quintet. So next time you watch the movie, take a look at that. It's Stephan's quintet. So I think that's good. This is another view of Stephan's quintet, except not through the near infrared, but through the mid infrared. And so you can, the point of showing it is you can get a lot of different information from the different wavelengths. And in fact, they could see that in the upper galaxy, that's an active black hole that's devouring material. And I don't know for sure, unless someone here knows or online, I don't know if that was known before this image, that was an active galactic nucleus. The next one, Southern Ring Nebula. This is an example of star death. So this is what will happen to our sun at some point in time. So this sun is collapsing. It's blown off the gases around the outside, what they colored to look lighter colored. It's the hydrogen that's blown off. And then the brighter on the inside, the blue hot stuff has been colored to look like the helium core is being blown off. So that's an image coming from, again, the workhorse NIRCam image on the telescope. Here's a comparison of it on the left with another image on the right with this NIRI mid-infrared. And you can actually resolve the two stars. This is a binary system. So you can see the brighter star there aside with the one that's dying. So that's what's being shown in that one. This one probably inspired a lot of screensavers, I imagine, around the Earth. This is the Carina Nebula, and it's kind of the flip side of the last one. This is star birth and not star death. So this is an area of galactic dust where it's being drawn together by gravity, probably shock waves coming through, driving stars to light up and form. So this is a star nursery in this page. And then one that isn't exciting to look at or pretty to look at, but I think was pretty incredible from a science point of view. One of the common ways that exoplanets or planets around other stars are found is called the transit method. So they just stare at a star, measure the light that's coming from it, and then when something passes in front of it, it'll dim for a little while. And then once the star passes, it'll come back to its brightness. Now, the ones that are found in this way are usually what they call hot Jupiters, which are really close to the star in orbit on a frequent basis, because you're not going to wait around 40 years for the next time to go around. So these orbit, this one in like, I think 3.5 or 4 days, it orbits each time. And so the instrument was able to see this decrease in light, the return, and then the repetition over time. Now that's not new, that's been around for a long time. But what's interesting about this first Webb image is that just as that planet was coming in front of the star, before the planet itself got there and only its atmosphere got there, they could use the spectrograph to take a look at that and say, well, what's in that atmosphere? And so they were able to take that spectrograph, compare it with known items, look at these different peaks and say, there's water in that, which is pretty incredible for a planet with like 5,000 degrees, right? It's got water in it. And it's sensitive enough, although I think they're still debating the data a little bit as to whether or not there's clouds in that atmosphere or whether it's just atmospheric water. So a lot that can be learned as the Webb looks at more of these exoplanets over time. This is a newer one, which you may or may not have seen. This is called the Cartwheel Galaxy. It was a galaxy that another galaxy punched a hole in the middle of it. Okay? So they're pretty rare ring galaxies. This one's doubly rare because it has 2 rings. But what really wasn't known as much before that I think scientists are excited about are the spokes in this cartwheel, these star forming regions, and how this gas is being lit up by shock waves and what other processes we don't know. So again, that's the workhorse NIRCam image of it. And over time, we're just going to find millions of advantages by being able to look at one thing with the different instruments on board, and sometimes working in concert with Hubble, where they'll both look at these objects at the same time to learn what they can. Okay, so where are we? We're long past the phase where the calibration programs on the instruments were done and the first images, which we've seen now. And so the next phase that we're kind of in now is what's called guaranteed time observations. So people that were responsible for building and developing and managing the telescope, they get first dibs on looking at things. I think part of it is a reward for, for doing that. The other thing is they know the instruments and they know its capabilities. So why not have them do some of the first work to see how it goes. Then it'll get into the general observation programs where people from around the world make proposals on what they want to look at, and there's a committee or a board that decides who gets time and when. And then there's what's called director's discretionary early release, which is not only the director of this program can also say, okay, so we got something we want to look at right now, so we're going to work our way into the schedule and we're going to do this. If a discovery is made by this telescope or others, they can kind of break into the schedule and say, we've got a short-term opportunity to take a look at something in particular, so let's break into the schedule and take a look at that. Okay. Don't expect you to read this, but there's copies over here if you want to know a couple of good sources of information for Webb stuff, whether it's on the web, Facebook, Twitter, or Instagram. There's some sites that I kind of like to keep track of. It's not super sciencey, but enough to kind of keep my science muscles in decent shape. And I think you'd enjoy it too. A lot of really cool